in science we encounter many parameters which are related by their rate of change. For example, rate of change of position is velocity, and rate of change of velocity with time is acceleration, like that. So if a parameter, the value of the parameter is given at a time t is equal to 0, and if we know the derivative or the rate of change of that parameter, we can find out the value of that parameter at a later time. So let us take the simple example of position of a body. Say position is 0 and we know the velocity, say velocity is 2, and what we want to do is we want to find the velocity after a time interval, say 2 seconds. We know that we have the straightforward equation, the new position x is equal to the old position plus velocity into the time interval, that is say after 2 seconds, then it is 2, right? So here we will get this 2, so this will be, but the answer will be 4. But suppose say we are not going to use this equation x naught into v into t, but we only utilize the equation, say the definition v is equal to dx by dt. That's the definition of the velocity, that is the time derivative of the position. Then we can do small steps, say after a time dt we can find out what is the new position. New position will be given by, say the new position will be the old position plus dx. Dx is nothing but v into dt. So that means the v is known. After a time interval dt, the new position will be the old position plus v into dt. So we reach the time t plus dt. Then again we repeat this calculation until we reach the required time, say 2 seconds. So this can be done. Suppose say we define dt is equal to 0.1 steps, and now we can write something like this. Suppose we want to repeat this calculation, that is x is equal to x plus v into dt, right? The old x is replaced by x plus v into dt. So this has to be done in a while loop until the time is less than 2 seconds, and after each step we update the time variable and finally ask the value of x. So save this as say x dot py or something, and now get a terminal. Say here we will run that, say python x dot py. T is okay here. What is the mistake here? T less than 2. Oh, okay, so we have not defined the initial time. T is equal to 0. Okay, it says 4. It is the same answer. If you want to see the initial calculation in between, put the print statement inside this, so it will show you after each delta t dt how it is changing. Finally it reaches 4. So this is actually a very crude way of doing it. We need not do it this way. We can use some better routines to do this. So Python provides you some libraries that will help you to do this, and before that let us do one thing. We can generate a graph using this, the position versus time. So for that we have to import the plotting library and the numpy. From pylab import star. So this imports numpy and matplotlib, and here we come, and so before entering the loop we will make two arrays. So put the initial value of time, and in this array we put the initial value of x. Then inside this loop we will, every time when we calculate a new value that is appended to the list, right? So we will have two arrays, and finally we can plot this TA versus XA to get a graph of position versus time. So here you can see it is a straight line, right? And not very interesting. So but let us take another case now. So here it is a constant velocity, and now we will take something like a totally different phenomena, that is, say, let us take the case of radioactivity. Like, you know that if you have a radioactive element, and suppose say there are n number of radioactive atoms at any instant of time, so the rate of decay, that is dN by dt, that how many of the atoms are decaying per second, that is given by, that is proportional to the number of atoms present, or it is minus L into N. So this equation is dN by dt is equal to minus lambda into N. This is the equation for radioactive decay. And we know the rate of change, and now we want to find out with time how n changes. You know that it decays exponentially, but let us see how it comes out. So here now let us take n is equal to, say, 10,000 atoms present when t is equal to 0, and our lambda let us take as 1, that is the decay constant, and dt again we are taking as 0.1. so here we keep an array, so time and the initial number of particles, 10. Now we want to see this for, say, 2 seconds or 5 seconds, whatever it is, and inside what we should calculate now, not this equation, this should go, and we have the equation dN by dt is equal to minus lambda into n. That means dN is equal to minus lambda n dt, right? So dN is equal to minus L n dt. So we also know now we have to update the n is equal to n plus dN. That means after a time dt, this old n has become this one, so it has changed by dN. In fact, because a negative sign, it has reduced. So every time then we have to append it to the list, so this new value is appended to this, right? So here again now TA versus NA. So this will give us a plot with time how this n is changing. Initially started with 10,000, so how it goes. So you can see here 10,000, it just goes down. Actually it's going down pretty fast. So here you can see it's almost reaching 0 within 5 seconds. So if you change this L to something like say 0.5, then run it again. Let's see what happens. So now you can see with 5 seconds it is decaying slower. So that means if you change the value of this decay constant, the rate of decay changes. So you need not do this again with this crude method, because Python provides you some libraries that does this sort of job. That means you can integrate an ordinary differential equation. This is an ordinary differential equation, right? So how to integrate an ordinary differential equation? You have to use a package called SciPy, and that has a module called integrate, and inside the integrate there is a function called ODE int. So first let us say from SciPy import integrate. Okay, so you get that, and now we have to define the function now, or let us say we just call this integrate.ode int is integrate.ode int. So first thing it will ask is what is the function, that is the derivative, that is this is differential equation, right? So let us define that as a function, like say define derivative is, and we put here say y, and we also have to put another variable t, even though we don't use it here, it is required for the solver. And the differential equation should return, actually that is minus lambda into n, right? And this n is this y here. So you can put any number. I think you can put an n here, and it doesn't matter, whatever this parameter value that you have to use here. So inside this derivative you give this function, and now here is give the derivative. This is the name of this function, derivative, and you have to give the starting point. Starting point is our this n, right? So not to be confused with this, even though there is no confusion for the program, but we will put it this way. And now the question is, now you have to give a time array here, like integrate from what time to what. Like you don't have to define it here separately like this. So we just have to remove this, and we make a array of time using our say arrange function. We can do that. Arrange start with 0 and say 1 and 0.1 step. So it makes an array of time coordinates, and that is passed on to this function. And what we'll do is we will see what this fellow returns, and it returns something which, so let us say print the result. So what all we have done now? So we know our equation is dn by dt is minus ln, and that is incorporated into this function. That this function actually what it returned is minus l into dn by dt, and we know that no, dn by dt is minus l n, right? So that is what it returns. So every time the function is entering, so it takes this fellow and returns its derivative, this first argument, and returns its derivative. So let us see what is the output. So it will be doing it in 10 steps here. So you see here, so 10,000, then it went. So every time, every step you can see it is reducing. So it does the integration, and the problem is it is returning it in a form, an array inside an array. It's actually a two-dimensional array. So before proceeding further, we should know a little bit of array indexing so that we can plot this. So we will start the Python interpreter to learn a little bit of the arrays defined by the NumPy package, because this Pylab imports NumPy as well as Matplotlib. So let us import NumPy, and first let us look at the one-dimensional array. Let us make a one-dimensional array. That can be done by a range function, say 0 to 15, 1, say a. What is a? You can see it is 15 element array going from 0 to 15 minus 1, right? Now you can index it, say first element, say the third element, like that. The array indexing is possible. You can also slice the array, say colon, say 9, 10. See what is coming up. So it starts with a of 5 and a of 10 minus 1. So it takes a slice between 5 and 10. So this is slicing of the array. And slicing you can do like this. One side, if you don't specify, it goes to the end of the array. On the other hand, if you don't specify the left side, it starts from the beginning, right? So this is how you slice and index a one-dimensional array. Now coming to two-dimensional arrays, how do you make them? First of all, we have that, you remember that zeros and other functions. If you give something like this, say 5, 3, you see there is a 5 row and 3 column. So a 15 element array, all initialized to zeros. So the problem is, now if you start indexing this, something like, suppose say if you take this is b is equal to zeros and b of 0, it gives one row, but you don't know which row it is. So we should have some numbers inside. For that we already have a array here, right? We can reshape it into a two-dimensional array. So reshape this a, and what is the shape we have to give? 5 into 3. Now what is b? Here you have an array, so that is 5 rows and 3 columns, right? It's a two-dimensional array. But if you carefully look at it, you can see it is like a one-dimensional array of a one-dimensional array. So you can see every element of a one-dimensional array is another one-dimensional array. So here this comma, the second, like that it goes. So that means if you do a b of 0, index the first element, you get this first one-dimensional array. If you do this, you get the second one, like that. So that is quite easy to get the, say, first, second, third row. But what we want is the column. Suppose I want to get the second column, what do I do? So let us do one more thing. Now get a particular element, say, you can see this is the second column and second row, third column, right? Second row, third column, you can find out in this 2D matrix. You are able to specify a particular element. But what will happen if you do the slicing here? You see, you get the entire row, that one comma, then you only put this, you don't put anything on both sides of it. You can do that as well, then you reduce it, see. But if you don't do anything, so you get this row. Now reverse the order. Suppose you put one here and a 0, no, just a colon here. What you will get? So let us have a look at the b again. See, this is nothing but the second column. So if you give like this, b colon comma 1, you get second. So if you do this, you get the first column. So you extract the column using this. So here you specify the column number, 0 for the first column, like that. So once we have learned this, we can come back to the result of this integrate. So result, we suppose put this result in something, and here actually it is a 2D array with only one column, but still it is formatted like that. So let us try to plot it. So how do we plot it? We have to plot by extracting the first column of this res. It will have only one column, so that time versus, that's a res of, what is our syntax here, a colon comma 0, right? So this, once this small trick is known, we can go back and plot it. So here this is how it is coming. So we are doing it only for 1 second. So let us do it for say 5 seconds. Earlier we did it for 5 seconds, right? Save. You can see you are getting almost the same result when you did it the other way. So this is a routine which is very powerful, that is solving these ordinary differential equations using this ODE into routine. So you can integrate. So all we know is the derivative. This relationship we know, and we know the value of the function at say initial position n. So that is given here. At t is equal to 0, the value of the function is this, and then t we provide an array, and it does the calculation for the entire array, that many steps, and give the result. So this is giving a two-dimensional array. For what purpose? The reason is this routine is actually quite powerful. It can take a set of differential equations. So we will, to demonstrate that capability, what we'll do is we will have two separate cases. That means, suppose say we have two different nuclei. Say one is only say 3000 and it decays a bit slower, and that is say n2, and it's lambda 2. What we want to do is we want to solve them simultaneously. So here the first argument now will become a vector instead of a single element. Time, of course, it will remain as same, and the starting point, now we call it as n0. You can give any name. That will have two elements, that is n and n2. So these are the starting points, and that we give it as n0 here, right? So other than that, there is one more change. Here we have to get a vector. So a vector, let us give a capital letter something, say give it as any name, say y, and now it has to return two of them. One is this y of 0, that is the first element, right? That is the n, and minus l. So to make it symmetric, let us call it as L1, N1, like that. So the first one is say minus L1. Okay, this is minus L1, right? So minus L1 n n1, that is lambda 0, then minus L2 into the second one, and I hope you understand that. So this is the first. So because y comes with the two elements, y of 0, that is for the first nuclei, and y of 1, that is for the second one, and each case this is returning this minus lambda into n, both cases. And of course the result will have now two columns, so we can plot both of them, right? So this minor change will result in what? So you can see there are two graphs. See, one started at 3000 and decaying very slowly, other one decaying faster. So you change this say to 0.2 and make it decay a bit faster. You can see that, this one, and or probably put both of them as 0.5 now. Let us see how it looks. You can see this is how it is. And if you consider this, when at 300, if you take this portion, this will be same, because now the decay rate is same. Okay, so this capability of this ODE int to accept a vector, I mean That means you can give say 100 differential equations, it will solve them simultaneously. That has another application. Suppose say you have a second order differential equation, so that becomes a bit tricky. Suppose let us take the case of a second order differential equation, say d square y by dx square, d square y by dx square, square y by d, something wrong with the editor, let us restart this. Gedit gave some trouble, so our file is what, x.py. okay, so d square y by dx square, say I'm just giving the equation as minus y, so this is my equation. D square y by, that means second derivative of y is equal to the minus 1 into the function. And now our job is the equation, the ODE int will take only first order differential equation. So the trick is you define a function, say dy by dx, a new function that is p. So you have one equation, dy by dx is equal to p. Alright, and this first equation now can be rewritten as dp by dx is equal to minus y, because d by dx of dy by dx, that is p, that will dy by dx of p is minus y. So you convert this first one equation second order into two equations, that is dp by dx is equal to minus y, and this p is nothing but dy by dx. Alright, so now all these n1 everything goes, so we have to get, first let us get the starting points ready. Starting point, so starting point we have to give, say first we give 0, that means our y at t is equal to 0 is 0, and say its derivative is 1. So this is our value of y at t is equal to 0 is 0, and dy by dx at t is equal to 0 is 1. Okay, so that's it. Now if you come here, this y will bring, you can see here you are passing, say you could take the first time when it is entering this program, it is this n0 will come with 0 and 1, and the first element, so y0 is our, here y0 is our y, and y1, this is our dy by dx of that, because we are putting the function, and the second one is the derivative. So now what it is supposed to return, it is supposed to return the derivative, right? And the y of 0's derivative is nothing but y of 1, that is how we are passing it, and the second one is, we know, the minus y. So this is how it will come. So we have two of them like this, right? It may take a little bit of time to understand what it is. So the first one, you are having the function y, and this derivative sh is already coming in the second argument, so that is y of 1 is dy by dx, so you just return that one, and the derivative of the dy by dx, that is our this dp by dx, that we know it is minus y. So let us run this and see what comes out of it. You can see this is the graph. So your original function y is going like this, and your dy by dx that started with 1, it goes like this. You can see this is a sine function and this is a cosine function, and in fact sine function is one of the definition of sine function is the second derivative is the function into -1. So that's the very basic definition of this function. So now you have seen how we can use this SciPy's integration routine, that means solving this initial value problem using the SciPy integrate.ode. So once we know this, that means solving a second order differential equation using this, there is a large number of problems we can solve. Like for example, mass and spring problem. You know, the force is minus kx. That is very similar to this, right? Here it is, if you take this as position and the second derivative, and suppose instead of dx if you put dt, that means acceleration, and it is nothing but force by mass. So it will be again the same form here. And another case is, suppose if you take a charged particle in a electric or magnetic field, it's again you can use the same kind of equations. So that probably we will consider in the next class, some of the applications, and we'll end this one here.